Initiative, the Climate and Society Initiative, and the Rutgers Energy Institute. And we're very pleased that you all are here this morning. I'd like to start out by thanking the program committee for putting together today's events. And I tried to write the names down so I wouldn't forget anyone, but it's Rachel Schwam, Jim Wright, Robin Lashenko, Ben Lintner, and Bob Kopp. And it's through their efforts that we've put together the program that we have today, which I hope you'll enjoy. And right now, it's my pleasure to introduce Dean Bob Goodman of the School of Environmental and Biological Sciences to give you some welcoming remarks.
So on the way back from New York last night on the train, I was trying to remember how many years this is. Is this the fourth of these? Might be fifth. So I remember the first one. The initiative has and the other activities, Climate and Society and Rutgers Energy Institute and some other things that have happened here at Rutgers have really performed admirably as a university-wide and indeed a statewide and regional convening agent for issues related to climate and energy, bringing together other related efforts, notably the two other sponsors. Since it began from a grassroots faculty-led initiative and a very broadly based effort, matters climate at Rutgers have really achieved a signature status at the university and throughout the state. Climate issues and energy have become one of the operating themes of our school. Also been adopted by our prior president, President McCormick, and I'll have something to say about the future in that regard in a minute. The challenges we faced persist and grow, as do the opportunities. Ahead of us, for example, is the integration of two medical schools and a school of public health from UMD. And especially in the lattermost case, the School of Public Health, I see a major opportunity for those of us in this community and others at Rutgers to contribute to building, for the first time, a top-ranked School of Public Health for New Jersey, which we decidedly do not have today. The $50+ billion punishment dealt to the region by Hurricane Sandy now needs to be translated into action plans on sea level rise, on energy resources, on a coastal protective plan, on zoning and land use, on tourism and fishing, on community resilience, on integrated climate science that can lead to further reliability in prediction, not just of events, but also confidence in climate trends on which we can base longer-term planning and investment. The list goes on, and it's large enough to challenge, but also provide very rich opportunities for a university as large, as diverse, and as great academically as this one is. Our new president, Bob Barchi, is launching a university-wide strategic planning initiative. The announcements about how we'll go about carrying on this strategic planning process, the first at Rutgers in many, many, many years, to be one of a kind, because I know something about how Bob goes about doing things. And I challenge you, students, faculty, staff, friends from other institutions, to engage fully in this planning process. Don't wait to be asked. Be thinking ahead, be thinking about how you would place matters climate and energy on the agenda of this university going forward, assuring a very strong showing and a strong place for the things that this community cares about and works on and knows about in the university's broader strategic plan. So this is a really timely meeting for a bunch of reasons, not just for what happened in the past 2 weeks to us, what has been going on here for so many years and has been growing into a really strong movement, but also the opportunity to help shape the future of the major strategic initiatives of Rutgers University going into the next decades. So thank you for what you do. Thank you for being here. Have a great day, and if I wasn't cultivating a $3 million endowed chair gift the rest of the day today, I'd be with you, but unfortunately I have to be someplace else. Thanks a lot.
Thank you, Bob, for those words of welcome and those insights into what's going on here at Rutgers. It's now my pleasure to introduce our first keynote speaker of the day. Kerry Emanuel is Cecil and Ida Green Professor of Atmospheric Science at MIT. He has a wide range of research interests, most notably tropical meteorology and climate, with an emphasis on hurricane physics. But his interests also include cumulus convection, the role of clouds, water vapor in the upper ocean in regulation of climate, and advanced methods of sampling the atmosphere in support of numerical weather prediction. Kerry has been on the MIT faculty since 1981. He was the director for the Center for Meteorology and Physical Oceanography, and more recently, the program in Atmosphere, Oceans, and Climate. He's received a number of honors, most notably member of the National Academy of Sciences, and in 2006 he was included in Time magazine's 100 People Who Shape Our World. We're very pleased to have this opportunity to hear what Kerry has to say today, and it's my pleasure to welcome him and introduce his talk on human effects on hurricanes, observational evidence, and projections for the next century. Kerry?
Well, thank you very much, Tony, and thank you all for coming under these rather dire circumstances here in New Jersey. Hurricane Sandy teaches us something important about climate, that the way people experience climate and climate change is through weather. Nobody really cares whether the global mean temperature goes up a few degrees. It's how climate change affects weather that influences us. So a question that I'm sure is on everyone's mind today, which I'd actually planned to talk about months ago before we knew anything about Sandy, was are storms like Sandy, are hurricanes influenced by climate change, and if so, how? Let me preface my planned remarks by saying that Sandy, at the time that she influenced this region, was no longer a tropical hurricane, but an event we call a hybrid storm, which is powered by two sources of energy: the classical source of energy for hurricanes, which is extraction of heat from the ocean. I'll say more about that later today. And also the classical power source for winter storms, which are fairly common around here, which resides in the horizontal temperature contrasts that exist on the planet. So what I plan to talk about today are, first of all, with respect to hurricanes, whose generic name, by the way, that scientific name is tropical cyclones, what controls their rates of formation on the planet? This is largely, unfortunately, an unsolved problem, but I think we're beginning to make progress on that. What controls the intensity of tropical cyclones? Why do they sometimes attain wind speeds of 200 miles per hour? What sets that limit? And what have tropical cyclones been like in the past, and how might they be affected by global warming? So I should begin with a very brief overview of the topic, which is the tropical cyclone itself. I'm sure you've all seen very beautiful satellite images of hurricanes. Here's one of Hurricane Floyd back in the 90s, and this has been doctored by the technicians at NASA to give it a kind of three-dimensional view. And when you look down from space, you see this massive cloud, several hundred miles across typically. And the densest clouds, tallest clouds, and the heaviest rain, and in fact the strongest winds are in a kind of a donut-shaped or annulus, often surrounding a clear, cloud-free eye like that. And as I said, a lot of the rainfall is in this annulus, but some of the rain is also concentrated in these spiral bands that you see around the center. These are thunderstorms that extend from close to the ocean surface all the way up to the tropopause, beyond which lies the stratosphere. So the clouds you actually see are at an altitude of between 12 and 15 kilometers, where the temperatures are in the neighborhood of minus 70 degrees C. So you're actually looking at ice clouds. One of the great and many ironies of hurricanes is that they form in some of the warmest regions we observe on the planet, and yet their tops are in some of the coldest places that we actually have on the planet. The upper tropical troposphere has temperatures that are frequently colder than you can find at the surface in Antarctica. And that's actually something that's relevant to why hurricanes are so strong, as you'll see in a minute. Here is a photograph from inside the eye of a hurricane. We've been flying research aircraft into hurricanes in the Atlantic region systematically since the 1940s. And these measurements are extremely valuable for research, but they're also important to make good forecasts of these storms. When you're in the eye of a hurricane, what you see, it's very difficult to actually describe what you see in a two-dimensional photograph like this. I keep thinking we should send an IMAX camera into a hurricane. But it's like standing in a coliseum, but the walls of the coliseum, rather than being 100 feet high, are 10 or 15 kilometers high. And the whole Colosseum is 30 or 40 or 50 miles across. So you see the nice blue sky of the stratosphere here. Often there's a cascade of ice crystals, like a waterfall, coming down the inner side of the eye. And then these very low clouds very close to the ocean surface are often filling the base of the eye. I think everybody should see this, so when I retire from MIT, I'm planning to start a hurricane safari operation. If you'd like to sign up, come and talk to me. This map doesn't come through very well on this projector, but this is supposed to show you the tracks of tropical cyclones over the period 1945 to 2006 around the world. So here's North America, here's Europe, and so forth. South America is down here. And I think you can make out these storms that form off of Africa, move to the west, and then curve off to the northeast. These are the storms that affect us. And the storms which by far we have the best records of. I mean, records of these storms literally date back to the fourth voyage of Christopher Columbus. Then there's this very active belt in the western Pacific. These storms coming in there, the records aren't so good, but we do know they've been around for a while. For example, Kublai Khan twice tried to invade Japan in the 13th century, and in each case was set back by typhoons, which is the origin of the word kamikaze in Japanese vocabulary, which means divine wind, which is what they called these storms because they saved them from the Mongols. And then there's a belt in the southern hemisphere going across northern Australia, the whole of the southern Indian Ocean. By the way, the Atlantic storms only constitute about 12% of the global total, even though they get 99% of the press. No storms within a few degrees latitude of the equator. Let's talk a little bit about the physics of the storms. I'm actually not going to talk so much about their physics per se as their energetics, because there's something quite nice about them. So one thing we can do with hurricanes is idealize them as being circularly symmetric storms. Sometimes they are almost circularly symmetric, and they can exist in kind of a steady configuration for time. So we'll pretend that a hurricane is invariant in time and circularly symmetric. Here's a cartoon, which is a vertical slice through a hurricane. The center of rotation is at the left here, and you're going up about 16 kilometers and out from the center 200 kilometers. And of course, the airflow is largely around the center of the storm, but there is also a component of the airflow which is in up, out, and so forth. So if you were to go, I would not advise you to try this, but if you were to go for a hot air balloon ride starting at A into B, you go whipping up the eye wall, and then over a period of several weeks come back down. Now, some of the people in the audience have probably had an elementary class in thermodynamics, and I'll speak to you for a few minutes. The others can take a little nap. The lurid colors here are a quantity called the entropy of the air. It's the entropy of a combination of dry air, water vapor, and condensed water, which are all assumed to be in thermodynamic equilibrium. The important thing is that it's loosely a measure of the energy content of the air. And the only way you can change it is by transferring heat from the ocean, here at the bottom, or losing heat by infrared radiation to space. Now you notice that as you go from A to B, this entropy increases. You go from blue to red, more or less. And that reflects the boiler room of the hurricane. The thing that's powering the hurricane, and this is a critical point, is the flux of enthalpy, or heat, from the ocean. And that occurs when ocean water evaporates. So we've all had the experience of getting out of a swimming pool or a lake. Even on a warm summer day, you feel cold, particularly if the wind's blowing. And the reason is that water's evaporating from your skin, and that process transfers enormous amounts of energy away from your body. That energy doesn't disappear, it gets added to the air, and that's precisely what's happening in the hurricane. Heat is transferred by evaporation from the ocean to the atmosphere. The fact that you can evaporate water from the ocean, that there's an evaporative potential, actually is traceable to the fact that we live in a greenhouse world. Because of the greenhouse gases, the ocean can't lose heat that it absorbs from the sun by radiating it to space, because the atmosphere is pretty much opaque to infrared radiation. So it has to develop a different way of losing energy, and it does that by evaporation. So it's the greenhouse effect, in a sense, that makes hurricanes possible. Now, when you get from B to C, you go up along a line of constant color, or constant entropy, and that's called an adiabatic process. No heat is added or subtracted. And then the heat that you acquired down here is ultimately lost up here by infrared radiation to space, and then you have another adiabatic leg. Now, it so happens that these four legs constitute the legs of a perfect Carnot heat engine, which was discovered by Sadi Carnot in the mid-19th century. It's the most efficient engine that's theoretically possible for converting heat energy into some other form of energy, operating between two fixed temperatures. It's a remarkable discovery by the French thermodynamicist in the middle of the 19th century. And nobody really thought that a perfect Carnot engine existed in nature, but this is one. For those of you who've had thermodynamics, this is isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression. Very, very efficient heat conversion to wind energy. And the efficiency of the engine is proportional to the temperature difference between where you're putting in the heat and taking out the heat. It's so cold, as I pointed out before here at the top of the storm, that this difference is enormous, and that's what makes hurricanes so powerful. So one of the things we worry about when we worry about climate change is how do you change the evaporative potential, which is the boiler room, and also what happens to this temperature up here? Does it go down or up? If it goes down, which is observed to be doing, that actually increases the power of hurricanes. Now, I'm not going to show you lots of equations, but I will show you one, and I won't belabor it for those of you who don't like equations, simply to say it exists, all right? It's the E equals mc squared for hurricanes. It tells us the maximum wind speed, which we call the V potential, in this case it's the maximum wind speed squared, is a function of things like the temperature of the ocean surface, the temperature at the top of the hurricane, and this evaporative potential. And that equation, which is developed from the Carnot cycle, it's a very simple equation for us anyway, allows you to calculate for a given climate state how strong a hurricane can be. So this is a map showing the solution to that equation, basically, as a function of how cold in degrees centigrade the top of the storm is, and how warm in degrees centigrade the ocean surface is. These contours are the maximum theoretically possible wind speed in meters per second. In the tropics, you're sort of in this range of 30, maybe minus 70 or so, a little bit more than 80 meters per second, which is in fact the strongest wind speeds that we observe in today's hurricanes. Remarkably, if you made the ocean really hot, and I'm talking about much hotter than we expect it ever to be, or the temperature at the top of the storm really cold, this equation doesn't have a solution. It's our equivalent of black holes. There's a singularity, and we have another kind of storm here called a hypercane. That's a conversation for a different day. We can map out in the present climate what this peak theoretical wind speed is over the course of a year. And this is what we see. We have peaks in the tropics of around 80 meters per second, about 180, 190 miles an hour. So you see that here in the Gulf of Mexico, in the Caribbean, and off the coast of Mexico, Central America. This is, in fact, the places where we observe strongest hurricanes. This energy argument doesn't know, however, that hurricanes are mechanically impossible at the equator. All right, so it's happy to give you a number at the equator, but hurricanes can't happen on the equator. Now, it would be nice if this theoretical potential intensity were just a function of the ocean temperature. And this map, this particular chart, is simply to demonstrate that that isn't the case. When you read articles in the popular press, sometimes even in the popular science press, there's sort of they'll tell you there's an equivalence between hurricane intensity and ocean temperature. But it's not true. So we can do experiments with climate models where we raise the ocean temperature by decreasing the trade wind speeds, which means that you have to have more evaporative potential. And then you get a potential intensity versus sea surface temperature curve like this, or by different means, in this case, changing carbon dioxide content, where you get a completely different slope. So the important message is that we know how to calculate this theoretical potential. We can do it if we know the climate, but we can't say it's just tell me the ocean temperature and that's all I need to know. That's not correct, all right? So it's not just a function of the ocean temperature. All right, well, what I basically tried to convey to you, and we'll come back to this point, is that hurricane intensity, we sort of know how to calculate a bound on it, and we know how to calculate that bound if we know the climate state. So for example, we can calculate from climate models how this bound is expected to change as we warm the planet, and as you probably guessed, it goes up, okay? But that doesn't tell us, that only tells us a piece of this puzzle. The other piece is what controls the frequency of storms. And this is called, in my profession, the Genesis puzzle, all right? That's not a biblical expression. It refers to tropical cyclogenesis. And it's not solved, okay? I always prefer talking about unsolved problems than solved ones. I think the unsolved ones are much more interesting. Well, here's some statistics that we get from satellite observations. This is the number of tropical cyclones over the whole world from 1980 to 2011. We can count these fairly easily with satellites. And there are roughly 80 or so of these storms every year on the planet, with a standard deviation of about 10. And maybe some hint actually of a decline in the frequency of storms, which is actually what we predict from models and theory, that the overall number of storms goes down a little bit when we warm the climate. Unfortunately, as you'll see later, this is no consolation for us. But the main point I want to make here is that my profession has no understanding of why there are about 80 storms on the planet. None. All right. If you asked a graduate student in my profession in the course of his or her qualifying exam, for example, write down on the back of an envelope an equation that sort of tells you the number of winter storms you would expect to see in a given climate, they could do a credible job of that. You can come up with an equation that says this should be of order N storms per year. Nobody has been able to do that for hurricanes. We don't understand this number. Why isn't it 1,000 or 10 or some completely different number? You know, we ought to be able to say that. Right now, we can't say that. So I wanted to spend a few minutes talking to you about some ideas that have been kicked around for this. And the first thing to realize is that tropical cyclones frequently develop from something called a cloud cluster. And I'll show you a picture of one so you understand what it is. Basically, it's a collection of thunderstorms. So we can back up one step and ask the question, why do cloud clusters form? How do they form? What determines their numbers? Well, here's a beautiful picture from 1985 of a cloud cluster over Bangladesh. And if you look at that from space, you get some idea of the scale because you can see the curvature of the Earth. This is a thunderstorm as seen from space. It's, it's about 10 kilometers across and 15 kilometers high. And you can see that this is a collection of thunderstorms. Maybe there's 15 or 20 in here, and that's what we mean by a cloud cluster. You'll notice a few other things. In the background here, you have this sort of hodgepodge or dog's dinner collection of thunderstorms and showers. This is what's typical of the tropics. You see this almost all the time in the deep tropics, a sort of a random collection. But once in a while, they all get their act together into a cluster like this, and you may also notice that it's unusually clear in a kind of an area around the cluster. Well, if this happened over the ocean, almost certainly this would become a tropical cyclone. But there's no ocean here, it's land. And if you remember from the Carnot cycle, there's no way of getting a tropical cyclone over the land. The ones that we have over land came in from the sea, of course, and in the process of dying. So what are the physics behind these clusters? If we understood that, I think we'd be well on our way to understanding the Genesis puzzle. Now, we have this simplest climate state that we can think of for the Earth, and it's called radiative convective equilibrium. It's a fancy term. It means that we're only going to consider a planet, or locally the tropics, where essentially we neglect any horizontal transfer of heat or water or something like that, and consider the climate state to be statistically one-dimensional. In that state, there are only two processes that transfer energy: radiation, both shortwave and longwave, and convection. These thunderstorms transfer a lot of energy. In radiative convective equilibrium, the convection's constantly heating the troposphere, and infrared radiation is constantly cooling it. And these two are in statistical equilibrium. That's called radiative convective equilibrium. In the last decade or so, we've been actually able to simulate these states of radiative convective equilibrium in computer models, and they're pretty boring looking. Here is a simulation in a model whose domain is about 1,200 kilometers squared. And you're seeing a snapshot here of the vertically integrated water vapor field. I could show you almost anything else like precipitation would look like this. And it's just sort of a random, just like I pointed out in that photograph of the cloud cluster, of what was going on in the background, sort of a random array of convection. It's exactly what we expected to see. If I were proficient enough to show you a movie of this, it would look like boiling water. Okay, it would just go on like this chaotically for a long time. So what? Not particularly interesting. But what we have noticed in just the last 7 or 8 years or so is that once in a while, for reasons we don't understand, the state will transform itself into one giant cluster. Now, these are run on something called a doubly periodic domain, so they just fold over itself infinitely. This is one cluster developing, and once that cluster develops, it's there. It's there forever. It doesn't ever go back to the other states. This is a dramatic phase transition in the character of this very simple climate, which was completely unexpected. Nobody had anticipated anything like that would happen. Now, one thing that happens to the atmosphere when these clusters form is it gets very dry. So this is a vertical profile of relative humidity from the surface up to the tropopause. For the classical radiative convective state, which is this chaotic state of convection, and then after one of these clusters have formed. And by the way, if you put those clusters on a rotating planet, they become tropical cyclones. In either case, the atmosphere dries out dramatically, a really, really big drying out. Now, we're beginning to think that what we're seeing here is kind of a thermostat, if you will, for the tropics. And so it really changed our thinking. Almost all discussions of how tropical cyclones behave with respect to climate are one-way discussions. The climate changes, what happens to hurricanes? But what we've learned in the last few years is it's a two-way street. The hurricanes themselves, they have a rather profound effect on the climate system. In other words, it's a feedback loop, and that we had not realized. So the idea, and by the way, we begin to see signs of this in observations. I won't labor. This is very new work done by some colleagues of mine in France, who look at the real world and show that the more clustered the convection is, these colored lines are for different degrees of clustering, the drier the atmosphere is. This, again, is a vertical profile of humidity. So we actually see signs that this is happening in nature. Now, through running a lot of these models, different groups of people have done this, we have come up empirically for what has to be true in these models to get this convection to aggregate. One is that the background wind must not change very quickly with height, a condition we call wind shear. We have to include the physics of the interaction of clouds with radiation. We have to allow the downdrafts associated with the thunderstorms to interact with the heat fluxes from the surface. And, this is very important, the surface temperature, which is specified in these simulations, has to be sufficiently high. If it's too low, the clustering doesn't happen. Here's an example of that. This is time here, and this is a quantity which is essentially the outgoing radiation at the top of the model as a function of time. When these clouds cluster, that radiation shoots up. And the reason is that water vapor is a very important greenhouse gas. If you get rid of it, which is what happens when these clusters form, you open up a window for photons to go right from the surface to space. So you get a big increase in outgoing radiation. Now, the only difference between these curves is the surface temperature. This is low surface temperature. This is a little bit higher, and so forth. In this model, there's a threshold temperature of about 25 degrees C, above which the convection aggregates and below which it does not. All right? So this is proving to be an extremely interesting problem. If you put this on a rotating planet, the clusters become tropical cyclones. You get what I call tropical cyclone world. It's just a kind of an array of tropical cyclones. We have some very nice scaling laws for that, which I won't belabor. But this feedback loop suggests a hypothesis, and that's all it is, that might start to bear on what controls the number of tropical cyclones. We know that at high temperature, the convection aggregates. And when that aggregates, the humidity drops. That reduces the greenhouse effect in the system, so it should cool if we allowed the surface temperature to react. But if it gets sufficiently cold, the convection disaggregates. That causes the humidity to go up, so the system warms up again. And all of this taken together means that the system is attracted to the state, just the critical state or critical temperature for aggregation. This is an example of what physicists refer to as self-organized criticality, where the system is attracted to the exact boundary of the phase transition. So it's a recipe for self-organized criticality. It was first proposed by David Nealon, although by a completely different mechanism. And the system should be near this critical state. And there's actually predictions that the theory of self-organized criticality makes, like the size of these clusters should follow some kind of power law distribution. So what we think is going on in the climate system, which is quite new, is that relates to hurricanes, is if we have some measure of how warm the system is, like the sea surface temperature here. There are various states of the system that are represented on this axis. One, the zero state, where there are no clusters or tropical cyclones. Then we have another state where you have lots of tropical cyclones or cloud clusters. And then we have an unstable solution down here. Between A and B, the system is metastable. That is, it's perfectly happy to reside in the zero state, but if you kick it hard enough, it might transition to this state. And that's what we think we're in. We're in this regime A to B, and that means that tropical cyclones don't form spontaneously. They're not observed to form spontaneously. They only form if some other weather system comes along and pushes the system up above this branch of the curve. For the mathematicians in the audience, this is a classical case of subcritical bifurcation, and we think that really does describe the real world here in this respect. And then you get a hurricane. But if we ever warmed up the system to B, hurricanes would form spontaneously, as indeed they do in models when we warm the system up sufficiently. So this whole thing is beginning to paint a very different picture of how hurricanes are related to climate and suggests that they're important regulators of climate in the tropics, which may explain why geological records constantly show that the tropics is much more stable than anywhere else on the planet, and somewhat more stable than most climate models think it should be. Okay, so this is a possible recipe for tropical stability. Now, having said that, let's look at what the hurricane records actually show. One of the metrics we like to use, so don't worry about this equation, is the power that hurricanes produce during their lifetimes. And it can be shown to be proportional to the cube of the surface wind speed. So we have this index, which is taking the cube of the wind speed and summing it over the life of each storm, and typically summing that over a basin like the Atlantic. And it's a measure of the total frictional dissipation of kinetic energy in the hurricane, and also a measure of the rate of generation. Now, we have good records of this in the Atlantic because of the aircraft measurements going back to about 1970. So this is an axis, don't worry about the units here, of power dissipation. It's going along at about 0.8 or so with some interesting oscillations. And then in about 1995, it begins to rocket up. And in the last decade, it's been about twice the level it was before. Okay, well, it's a pretty big number, a factor of 2. Hurricane energy in the Atlantic is about doubled in just in less than a decade. Why did that happen? What's going on there? That's a big signal. What's happening? Is this global climate change? Is it local climate change? Is it random variability? Well, here I've done something. I've simply overlaid on that same curve the temperature of the tropical Atlantic Ocean during hurricane season. Temperature is not potential intensity, as I mentioned before, but it's much better measured. We have robust measurements going back more than 100 years. And there's this amazing correlation between hurricane power and ocean temperature. In fact, the regression coefficient squared, the correlation coefficient squared is 0.87. It's a very, very big correlation for 2 completely independent measurements in a geophysical system. And theoretically, there should be some relationship between the two, but we expected neither that it would be that close or that it would be that sensitive, in the sense that about a 0.5 degree C increase in ocean temperature led to a doubling of hurricane power. What's going on there? Now, one thing we can do is use this linear regression between these 2 time series and make use of the fact that we have good ocean temperature going back 100 years or so before this, and say, well, what if we use the ocean temperature measurements to hindcast what hurricane power would have been like in the past? Then we get this curve. It's a bit of a dangerous thing to do. Just because you see a relationship for 30 or 40 years doesn't mean that it necessarily existed before that. But we're just going to be brave and do it anyway. And I'll tell you why I've tried to be brave that way. You get this curve for hurricane power. We call that predicted power dissipation, starting out at about 0.5 in the early part of the late part of the 19th century, early 20th century, shooting up into mid-century, dropping off into the 70s and 80s, and then rocketing upward as we saw before. That's a very interesting curve. There are these short period oscillations. If you look at that, if you squint and look at that, it turns out that the average period is 11 years. Does that ring any bells with anyone? Solar cycle. Well, that's of course what we thought, and we tried to pin it to the solar cycle. It turns out not to be coherent with the solar cycle, oddly enough. But that was our thought. We still don't know why there are these oscillations. And then there's this sort of what looks like it might be an oscillation on a longer time period. We'll come back to that. All right. Well, should we have any faith in that? Let's go back to the historical hurricane records and ask, even though we don't really believe them much before 1970, let's just do it and plot on the same diagram the so-called observed power dissipation. Well, there you have it in red, all right? So you have the SST predicted power dissipation in blue. The observed in red, nobody really believes these hurricane observations in the earlier period, but aside from this period right here, they actually line up very well, including the shorter period oscillations. So that gives us some confidence that maybe, yeah, we really do see hurricane power increasing pretty rapidly in the Atlantic. This period here, from 1939 to 1945, might ring some bells too. Of course, it was the war. And during that period, we relied on ships at sea a lot to report hurricanes. Of course, ships didn't purposely go into hurricanes, but they accidentally wandered into them before the days when we got good at warning them off. But in the war, two things were different. First of all, ships were not allowed to transmit information by radio. There was radio silence in force so that the ships wouldn't be detected by submarines. And ships traveled in convoys across the Atlantic, which turned out to be a very good strategy for avoiding submarines, but a very poor strategy if you wanted to sample the Atlantic Ocean. So we think there was perhaps an underestimate of hurricane power then. And if you look at modern records, the power dissipation, this is sort of a contour map, power dissipation, a lot of it's in the Gulf of Mexico, the Caribbean, and in the far western Atlantic, where we always had a lot of ships historically. So maybe they weren't so badly measured after all back then. So we're left back with this record and trying to explain it. You know, it's a bit alarming because we're not seeing 5% changes in hurricane power. We're seeing order 100% changes in hurricane power, and hurricane power is closely related to damage done to human structures by hurricanes. So it's a bit worrying. Okay, this is just a summary. Tropical cyclone power dissipation has more than doubled since the 80s, with only a 0.5 degree increase in ocean temperature. There's other evidence. I think I'll skip over that and get to the point, what's causing the changes in ocean temperature to which hurricane power is so beautifully correlated. But we do know something about that. Here is a record going back to the end of the 19th century of the August through October sea surface temperature in the part of the region that forms hurricanes in blue. Now this curve differs from the one I just showed you because I've smoothed it with a 10-year running average to get rid of those smaller wiggles to emphasize the bigger pattern, okay? And I've subtracted the long-term mean, so it's centered at 0 degrees C. The green curve is exactly the same exercise, but rather than just the tropical Atlantic, it's the entire northern hemisphere. Land, ocean, everything. And the point is that there's not much difference between the two. The tropical Atlantic in summer is not doing anything on the decadal timescale that's appreciably different from the northern hemisphere. And so in some sense, we have a simpler problem to ask, why did the northern hemisphere execute this seesaw pattern with an upward trend, all right? Well, of course, a lot of climate science is devoted to questions just like this, and we know something about that, it turns out. We'll back up one further step from the northern hemisphere to the planet. And if you look at the whole planet, you see some of the same signatures, warming in the early 20th century, a leveling out in mid-century, and then an increase. Well, this is the same curve again, the global temperature relative to its value in the year 1900 observed. And this beige curve is that same thing modeled by climate models, a whole variety of climate models. There's actually error bars, which are miraculously missing from the screen, although I can see them on my screen here. There's an envelope here. But the climate models do a pretty good job in replicating this trend in this sort of seesaw. But with the models, we know basically what caused the model's temperature to change. And there are 4 major factors which are shown by the colored curves down here, relative again to their long-term mean. 2 of them are natural, solar variability, which had something to do perhaps with the increased temperature in the early 20th century, volcanoes, which cool the planet. And there was a statistical lull in volcanic activity from 1918 to 1960, which also allowed the planet to warm up in this period. Then there are 2 man-made effects, the greenhouse gases, shown by the blue curve here, and sulfate aerosol pollution, which causes a kind of haze that reflects sunlight, cooling effect, shown here. And so we have a picture now of this, about what caused it. In the last 30 years of warming have been dominated by greenhouse gases, but before that, basically a lot of these factors contributed to temperature change. It's not simple. Now, there's one key point here, that the sulfates are a little bit different because they're focused in the northern hemisphere. The rest of these things are pretty global. Sulfate aerosols are concentrated near their sources, which are mostly industries in the northern hemisphere. And so a few years ago, Mike Mann, who's at Penn State, and I published a paper suggesting that the difference between the global temperature and the northern hemispheric temperature could be largely explained by the sulfate aerosol forcing. So here is a record of the global mean surface temperature again. This blue curve is actually the temperature of the tropical Atlantic, but we've seen that that's similar to the northern hemisphere temperature. And then this light blue curve that starts at 0 and starts to go down is the cooling effect of sulfate aerosols. So Mike and I asked a simple question: could we explain the northern hemisphere by adding the aerosols, this light blue curve, to the global temperature, the red curve? And yes, you can. So this red curve is now the sum of the global temperature and the aerosols, and the blue curve is the Atlantic temperature, and on the decadal time scale that does very well. So if that's right, this seesaw pattern is not an oscillation. A good mathematician would never conclude that he or she was looking at an oscillation based upon 2 peaks and 1 minimum, right? Doesn't stop meteorologists doing that. But just an accident of the way radiative forcing has changed over this period. So this increase was driven somewhat by an absence of volcanoes, a little bit of solar forcing, and a little bit of greenhouse gas forcing. This decrease was a man-made decrease. It was sulfate aerosols. And then we passed the Clean Air Act, and the old Soviet Union, which was a great producer of dirty air pollution, collapsed. And those two together, plus the continued assault by greenhouse gases, is what led to this increase. So I like to say that our hurricane problem is partially attributable to the Clean Air Act, but no, I'm not arguing it should be repealed. It was a black lining on a silver cloud. Now I want to end by talking about the future, as far as we understand it. We've developed a technique. I know we started late, Tony, and I don't know whether you want me to try to finish now or 5 minutes. Is okay? Okay. We've developed a technique for trying to infer hurricane activity from global climate models. Now, global climate models are integrated on computational meshes, which are too coarse to simulate hurricanes at all well. They get something that looks like hurricanes. So what we do at MIT is we take the output of these climate models and we run within those climate models, very detailed hurricane models that are very high resolution, coupled to the ocean and so forth. And here's how it works. We take the climate state as represented by the climate models and we seed it randomly in space and time with proto-hurricanes. It's like going down to the greenhouse store and buying a package of hurricane seeds and just throwing it randomly into the climate model. That's pretty much what we're doing, okay? And we then ask, where do these seeds move? And that turns out to be an easy problem. They move with a large-scale flow predicted by the climate models. Then the key step is we run this detailed ocean atmosphere model over each of those seeds. And we note how many of them achieve at least tropical storm strength and discard the others. So this is a kind of a method of random seeding followed by natural selection or survival of the fittest. The seeds you put in the bad places, which in practice are about 98% of those seeds, which is similar to my success rate as an amateur gardener, die, okay? And the 2% survive. But we can do this enough times to create data sets of literally hundreds of thousands of synthetic storms that are consistent with that climate state. Okay. And here's an example of just 200 synthetic tracks in the Atlantic. We do this globally, by the way, but I'm showing you here the Atlantic. Colors have to do with intensity. We can do all kinds of statistics on those tracks to compare them to real storms. So here's one. This is just a number of events per millennium that exceed the wind speed that you see on this axis. So the stronger the storms, the fewer of them there are. The red comes from the synthetic technique. The blue comes from observations of hurricanes beginning in 1950. And we actually get a very nice intensity distribution, which is important. Once we have that, we can apply this technique to try to understand hurricanes in different climates. So here's I know you can't see that very well, I'm sorry about that. This is an application of a climate model simulation of the present climate. And this for the climate about 3 million years ago, called the Pliocene, which a lot of people think is a good analogy to where we're headed. It had same configuration of continents pretty much as we have today, but there was no ice in the northern hemisphere. The carbon dioxide content was very similar to is right now, about 360 parts per million. Actually, we've gone beyond that now, but I don't know how well you can see that, but there are a lot more tracks in the Pliocene than there are today, according to this downscaling, in all the ocean basins, not just the Atlantic, but Pacific as well. We can couple these synthetic tracks to surge models, and here is a graph from a paper that we published in February with Ning Lin, who's now down at Princeton, on the faculty of Princeton, showing one of the synthetic events whose track came right up over where we are here in New Jersey. And this is the maximum surge height that was predicted to be associated with this event. It so happens it looks quite like the surge we just had. So in some weird way, we didn't know we were doing this. We forecast Sandy's surge. It was the actual surge of Sandy in this area looked pretty much like this, about 3 meters at the Battery in New York, due to the wind component of the surge. So we can do that, and now that we have that technique, we can apply it to global climate models. And this shows the percentage change in power dissipation in 5 parts of the world, the Atlantic, Eastern Pacific, Western Pacific, and so forth, for downscaling 7 different climate models. And unfortunately, as is true for everything you look at having to do with the regional predictions of climate models, there's lots of change from one model to the next.
This is change between what and what?
Sorry, thank you for asking. It is the change between the last 20 years of the 20th century and the last 20 years of the 22nd century under emission scenario A1B. It's a moderate emission scenario. And so we see big changes, but not necessarily agreeing on the sign. So 2 of the models actually produce decreases in the Atlantic. They all agree about the Pacific should increase, and most of them agree that the southern hemisphere should go down. And unfortunately, that's the level of uncertainty that we have to live with for the moment. If we average over the 7 models, we see that the sort of consensus is an increase in formation rates in the Pacific, Central Pacific, a decrease around the Philippines and the Bay of Bengal, an increase in the Arabian Sea, a decrease in the southern hemisphere, and in the Atlantic, a northward and to some extent eastward shift in where tropical cyclones form, which turns out to be bad news for the northeastern part of the US. And this, going back to our February paper, is the prediction for the changes in probability of storm surges. This happens to be for New York. This is, again, for this scenario A1B, but meant to be the last 20 years of the 21st century. So this is the current climate. This is surge height, return period, and the average interval between storms in years, and for a future climate. And these are 4 different climate models. They all produce a big increase. So for example, this French model, the Sandy magnitude surge went from once in 1,000 years to about once in 100 years. Now, is Sandy an example of that? I have no idea. You can't make an attribution to a single event. But these results, which were published in February, suggest that surges in New York should become more probable going forward. All right, I think I'm going to skip this part because we're so low on time and just go to the summary. Hurricane activity is clearly sensitive to climate. We see that in models, we see that in observations. We don't entirely understand it, it would be fair to say. Hurricanes and cloud clusters in general, however, may help to regulate the climate. It might not just be a one-way street by drying the atmosphere and cooling the surface when it becomes too warm. This very simple downscaling, which I just described, also confirms that hurricanes are fairly sensitive to the climate state and suggests that we should see, by and large, an increase in the frequency of destructive hurricanes over the next century globally, although a diminution of the incidence of weak hurricanes, which typically aren't very destructive. So that's kind of where the profession is at the moment, and I'm happy to answer your questions, of course. Thank you.
for some questions. So if you have some, just raise your hand. We have a mic. Great. Someone will bring over a mic. And Alan.
It's just a point of clarification. When you talked about the drying of the troposphere when you have hurricanes, was that including in the hurricanes, or was it just outside the
It
hurricanes?
was including the hurricanes. Hurricanes don't tend to cover that much fractional area of the domain, so we included the hurricanes there.
When you said feedback loops, I thought negative and positive. So could you use a negative or positive word with that feedback loop?
That's a negative. That particular feedback's a negative feedback. It means that hurricanes, if we're right about them, and cloud clusters in general, like the one I showed you the picture of over Bangladesh, are they're kind of a response to an overheated tropics. They're trying to dry it out and thereby cool it off. And that, I hope that's true, but it doesn't, unfortunately, help us with the middle and high latitude climate problem. Middle and high latitude climate geologically has been very unstable. While the tropics are kind of rock steady, we see huge variations, and the ice ages are a good example of that. But this may help explain why the tropical climate is relatively stable.
So Mel and then Mike.
No, you just answered my question.
Okay.
Thank you for an extremely clear and illuminating talk. I understand better now why it's not possible to attribute a particular storm to climate change, but I also understand better that climate change and the frequency and intensity of storms are related. So my question has to do with the appropriate and effective way of communicating this to the public and what your own perspective is on this. I don't like to call it, it sounds horribly patronizing to say teachable moment, but maybe learnable moment for society in the face of what just happened with Hurricane Sandy.
That's a really, really good and very tough question that my colleagues and I talk about what you just said all the time. How do we do this? And, if we are going to be true scientists, we say it's just not possible to attribute any single event to a cause. But at the same time, you're right that it's a teachable moment, that it reminds everybody how vulnerable we all are to natural phenomena. And we like to use occurrences of events like Sandy to remind people that the statistics of these events, when looked at over decades, do show reasons to be concerned about their increased incidence, and that theory and models of climate also suggest that the probability of events like that is going to go up by amounts that we wish we could be confident of. But, the whole problem is that science is uncertain, and people who are used to addressing risks are always coping with uncertainty. And you have a probability distribution of outcomes, but the consequences to us are extremely asymmetric. When you go from the benign side of that probability curve with almost no costs to the far side of that probability curve, which are catastrophic to our descendants, that means that you have to take into account that asymmetry when you assess risk. Reasonable people will differ about the extent to which you should try to curb those risks, but certainly to argue that there's no risk, as some people do, or that we should do nothing is scientifically and morally indefensible at this point.
Two questions. Could you explain mechanisms by which the cloud clusters lead to drying? And secondly, on your bistability diagram, so give a sense, or can you even say, given the simplicity of the model, where those A and B points are and how much warming before hurricanes start responding instantaneously?
Yeah, those are good questions. So what happens basically when clouds cluster is that they precipitate much more efficiently. They're not actually producing more precipitation that's constrained by other things in the system. But in other words, the average raindrop that falls in the normal radiative convective equilibrium loses roughly half of its mass on the way down to evaporation. That moistens the air. In the cluster, the raindrops are falling through saturated air, and they don't evaporate. So the air coming out of the top of the cluster is basically lost all of its water to rainfall, and then that subsides. It basically produces almost no humidity. By the way, we can talk about this later. That also implies there's a strong should be a strong isotopic signature in rainfall. It should be very different in clusters than it is in ordinary tropical rain. We actually see that signature. Geochemists see that signature. We don't really have a good feeling for where those bifurcation points are. The models, the cloud resolving models, differ, but sort of on the order, that B point is sort of on the order of 30 degrees or so, plus or minus 3 degrees, we think. But at this point, it has to be considered a rough estimate.
Did you say 30?
30 degrees C or so for sea surface temperature. Yeah. Well, again, it's choose your model. There are some models where it's 35.
Sandy was a hybrid storm, and
Yes.
Do you have any thoughts about, whether there's, I have no idea whether there's much of a record of such storms, and also whether the changes in the Arctic, ice melting and so on, could somehow be increasing the frequency of hybrid storms?
Well, I'm glad you asked that question. Hybrids are very interesting. We only identified them as their sort of own subclass of events 20 or 30 years ago. And my profession hasn't really done its homework on this. And I put it that way because I think the data exists in historical archives or reanalysis data sets, and also in climate models to now go in and say, what have hybrid events done in the past? What do models suggest they'll do in the future? We just haven't gotten around to it, which is too bad. I think Sandy, if there's a silver lining on Sandy, is it's going to stimulate a lot of my colleagues to do that work. Okay, and there was a second part of your question.
Whether changes in the Arctic could conceivably be influencing that.
I don't know the specific answer to that question because I haven't looked at it, but generally, when we look at this problem of hurricanes, we have to be very cognizant of how their tracks might change from climate. That has largely to do with how the general circulation of the atmosphere changes. And so you can even have scenarios where, say, the number of storms in the Atlantic goes down, but the number hitting the East Coast goes up because their tracks change. And things like changes in the Arctic will have a strong influence on that. So it's certainly something to pay attention to. Yeah.
So we have time for one more question. Yes.
A question on, you had that nice power dissipation index correlating to the sea surface temperature graph in the Gulf and the Atlantic. I know in one of your papers you had mentioned that there wasn't quite as tight a correlation in the Pacific, and I was just wondering if you could comment on that and what that might mean globally.
So we don't really see that kind of correlation anywhere else in the world when we look at it. The reason that we had looked at it in the Pacific is that we used to have aircraft observations from about 1945 to 1987 when they were discontinued. But we've never had aircraft observations in the eastern part of the Pacific, in the Indian Ocean, or in the southern hemisphere. And we have to rely on satellites to estimate hurricane intensity, and that we can only do since about 1980, and very poorly at that. So you're right, it's not terribly well correlated in other parts of the world as it is in the Atlantic, but we're not quite sure how much of that is real and how much of that is just because we're not measuring them well. So it's an open question. Yep.
Okay, and then I guess with that, what I asked the panel to do, and I'll just quickly introduce our panel: David Robinson, professor in geography and also New Jersey state climatologist; Ken Mitchell, also a professor in geography and a specialist on natural hazards and the human impacts of natural hazards; Carrie Emanuel, you've already had a nice introduction from him, our guest speaker from MIT; and then Ken Miller, professor in Earth and Planetary Science, who is an expert on the topic of sea level rise. So what I did, I sort of thought about how can we do this and make this sort of efficient and give plenty of time for the audience to engage, is I asked each panelist to think about just sort of a 1-2-part question that I want them to maybe just go down the line and have them address that 2-part question, and then after that just open it up to sort of audience questions, audience comments, and sort of have a little bit of a discussion following that. So the question I asked was, Part A, what surprised you most about Hurricane Sandy? From your experience as your position of scientific expertise, what was the issue, or what was some facet that really surprised you the most? And then what do you see as some critical lessons that we need to take away from Sandy and take away from this event? So if I can shift it then, do you mind starting out, Dave, with that question?
Do you want just part one, and then we'll go around to the second part?
Okay.
How do you want to do that?
You guys are nodding, you guys like that?
Sure.
Okay, part one and then part two, and then but you can't talk too long because we got to let these guys answer questions.
And you started with me?
Oh, yeah, I know.
Extreme, I'll tell you, in a lot of respects, there weren't a lot of big surprises when you look back 10 days before it and you saw forecast models that suggested this event was going to take place. But I guess thinking back to the surprises, it was probably the magnitude, the extreme nature of several aspects of the storm. One was the barometric pressure. We shattered the state record for the lowest barometric pressure on record. 946 millibars, if that's verified, would equal the Category 3 hurricane of 1938 that just decimated and destroyed Long Island and southeastern New England. So we didn't have the winds of a Category 3 storm because it was spread out and the gradient wasn't as large. So that one, a hidden little extreme in this storm, Cape May County had a foot of rain. I don't think many people realize this. It's about a 200-year return event for a 2-day storm down there. So you had the rain, and then the storm surge exceeding 3 feet over the previous record at Sandy Hook. So it's probably, we knew the storm was coming, we knew it would be strong, but it was the extreme nature of several of these different variables that was really so surprising.
Like Dave, I don't think there was anything on the large scale that I would call, like Dave, I don't think that there was any large-scale surprise for people interested in the human impact side of the disaster. I mean, just like there were many who saw disasters waiting to happen in the area of New Orleans before Katrina came along, there were plenty of people who saw similar disasters waiting to happen in the northeastern United States, and mostly because of the increases in human exposure and vulnerability to existing levels of severe storms. And the fact that we got a more severe storm merely added to that effect. But if there's a small surprise, I think, or a smaller surprise that I would see, is that there didn't seem among the worst affected communities to be much difference between those communities that had spent a lot of effort trying to reduce their flood risks and those that had spent much less effort. They were equally badly affected. And I'm talking about the worst communities here, not ones that got away with little or no damage. If you look at something like the community rating system for the National Flood Insurance Program, which gives you indicators of how hard communities are working to put in place protection against storms, you'll see that a place like Mantoloking, which came off very badly in this storm, was doing relatively well on the scale of working to reduce losses, whereas there were some other communities that weren't really doing anything at all, in fact, barely participating in that program. So what that suggests to me is that the standards that are used for deciding what is an effective level of protection probably need to be raised right across the board.
I don't have very much to add, except that the big surprise for me came about a week before Sandy when I looked at the weather maps, particularly the forecast maps from the European Center for Medium Range Forecasts, and saw something that I think some of us didn't think was even possible, and thinking at the time that something went wrong with the model. But then when successive forecasts showed the same thing, we understood that we were going to see an historic event here in New England. I think in hindsight, what surprised me was how beautifully well this storm was forecast from a meteorological perspective. We kind of knew what was coming a week ahead of time. And that's really an amazing accomplishment for the profession of numerical weather forecasting. I will say that if you assembled a group of my colleagues, weather forecasters, numerical weather forecasters, and so forth, into a small team with the diabolical mission of inventing a storm that would maximally damage New Jersey and New York City, I don't think we would have come up with anything that was very different from Sandy. It looks very much to us at the time like a worst-case scenario.
As a geologist, there's no surprise that barrier islands are severely impacted, and Long Beach Island had inlets in it that were mapped by Henry Hudson on one of his early voyages, third voyage. But as a human being, I was surprised at the extent of the damage. In the Ash Wednesday storm of 1962, an inlet opened in Long Beach Island on 79th Street and Harvey Cedars, and that was considered rather catastrophic. We've all seen Manaloking Bridge, where that inlet was quite dramatic. But there were also numerous places where the ocean met the bay, where full inlets didn't form. At least two were reported in Beach Haven and two in Ocean City. And the extent of the damage going from the Battery all the way to Cape May and the amount of flooding, various reports, obviously, that you heard about Sandy Hook tide reaching a maximum. But you don't know that tide gauge was broke and went offline. The amount of flooding at Atlantic City and other places, I have a shore house, and it was 19 inches above the previous three major northeasters that we've had in the past 20 years, the perfect storm of 1991, the December northeaster of 92, and the October 2005. These were all so-called 100-year events. But on the ground, we were really affected. A lot of my neighbors are homeless in Waretown, and we were down there this weekend, and it can only be described as a war zone. And the big surprise, to tell you the truth, is that there wasn't more loss of life. I can't say that we were lucky to only lose 40 people during the storm, but it could have been so much worse.
Okay, so I think that was really a very powerful assessment of some of what we're hearing and what we're learning. But I'd like to also then just see if we could go through our speakers one more time and just ask them to think about what can we take away? Give us something to take away.
The opposite direction.
Oh, opposite? Do you want to start there?
Sure. What will we do? We're going to rebuild. We're probably going to rebuild basically a little smarter. We won't allow houses to be built on ground level. They're going to be required to be on pilings, but they're still going to be in harm's way. Federal flood insurance will allow us to do this. It'll allow us to subsidize welfare for millionaires. What we should do is raise our flood level standards, at the very least for towns like Waretown, where I'm at. The DEP has already raised the flood standard a foot above federal, and that was considered controversial. We should raise it more, and there should be a discussion amongst various people, from coastal engineers to the Army Corps of Engineers to scientists, as to what that actually should be. And we should have a conversation, and that conversation should be whether or not we should adopt the same policies for the coastline that we've adopted for some of our rivers. Most of the people here are familiar with the town of Bound Brook and familiar with the town of Manville. And you know that those towns have been severely affected by river flooding, as has portions of Trenton, and that those people who were affected by a storm and floods in 1 year rebuilt only to be flooded out the next year. They were covered by federal flood insurance, but the decision was made, it was more effective to buy those people out and basically develop it into parkland. Should we be doing that for some of the New Jersey shore?
I can do very little more than second what you just heard from Ken. I would hazard to say that in 2 weeks' time, everybody in the United States, almost everyone in the United States outside these affected areas will have forgotten all about Sandy. And in a few years' time, unfortunately, even here, they'll have forgotten about it. This is just the lessons we learned from previous storms. So there's a huge gap, as Ken said, between the lessons we ought to take away from this and the lessons we will take away from it. So the big problem in the United States, and you don't see this in many other countries in the world, is the enormous extent to which we subsidize people to live in and build in risky places. And the migration of the U.S. population from less risky to more risky areas is astounding, and it's the 6,000-pound gorilla in the system. And there is no political will that I've ever been able to discern to change the system. And so I think we have to say that the lessons we should learn won't be learned. The real lesson is that we've set ourselves up in this country for a string of Katrinas and Sandys going as far forward as you care to imagine.
Well, I think that one of the things that I would want people to take away is an appreciation for what you can learn by looking at other times and other places where people faced similar problems. And of course, the other time that they faced these problems in New Jersey was in 1962, which has been alluded to here. And what happened after the 62 storm was that in that interval, until the next census was taken, the population of all those impacted areas increased very dramatically. In fact, its population, the permanently resident populations today, aren't much different than the permanently resident populations in 1970 were, but the 1970 populations were significantly larger than the 1962 populations. So what the storm did was it cleared the ground for a new phase of development of the Barrier Islands. I heard the governor the other day speaking very emotionally about the loss of his childhood memories on the Jersey Shore and alluding to the fact that the Jersey Shore area that was most affected was a family shore. And after large disasters around the country, not just storm disasters, but other kinds of disasters, it's quite common for those who have the ability to mobilize large amounts of capital to move in and recreate the area on a much larger scale investment basis, where all the units are larger and corporate resorts replace family resorts, that sort of thing. So I think you'd want to remember that sort of lesson as we contemplate what we should do in the weeks and months that are coming up. And we have some lead time in some parts of the Jersey Shore because of the long period that will be required to replace infrastructure such as the underground gas lines. But this is something that's happened elsewhere, and it has all the earmarks that it may happen in New Jersey again, and the family shore may disappear without some very careful regulation in the interim.
I've positive and negative lessons learned. I think one lesson learned was it could really be that bad. I think in the past people didn't appreciate, they thought they had seen the worst. And despite some of us saying they hadn't, they now understand that they've seen something worse. But it could be worse. This was a perfect scenario for this particular storm, but what if the winds had been 20 miles an hour stronger? You think the power grid of this state suffered from this storm? It would have almost incalculable what would happen there. So that's a lesson to learn, that we saw what nature can do more than we'd ever seen for most of the residents of this state, despite all these vignettes for the 50th anniversary of the 62 storm, and I gave multiple interviews back in March about that. It was still kind of an historic thing. Well, now we've all seen it, and hopefully it will stick in our memory banks, and we'd be prepared if it's worse. Could be worse. Another thing that I always try to drum home is that we've seen that it's not only the water, it's the trees. And the fact is, more people were killed by falling trees in this storm than by drowning in New Jersey. And each year, more people are killed by falling trees in this state than any other natural calamity can provide, although they're one here, one there type of things like lightning deaths. But we've got a wonderful, rich forests around our state and around our homes and such, and that hopefully there's a greater appreciation there for that. And then finally, on a positive note in many respects, good forecasts plus excellent emergency management people out there in the local, county, state level, the public attention to the forecasts and management through the media, through the emergency management forecast, equals lives saved. And in some respects, some property saved. You can't move your house, you can move your car and such. And I think that's a great lesson learned here. We got a little primer in that when Irene came along just a year ago, August, and people really adhered to evacuation orders for the most part. I think a saving grace in part with this storm, those who didn't leave by Monday for this storm saw the first high tide on Monday morning. And they listened and heard, this isn't supposed to be the worst one. We better get out of here. This is going to be worse than Irene along the coast. So maybe that helped with saving of lives. But to do all of this, and this is terribly self-serving, you need resources. You need resources to monitor the situation, to produce better forecasts, to have better emergency management and such. So hopefully the lesson learned is we can't take any of this for granted. Most of us made it through, some with tremendous hardships that are going to go on for years. And let's see what we can do to maybe weather the storm a little better next time around, because there's going to be a next time.
Okay, thank you so much for the panel making their first round of comments. And then I thought what we would do is just really give the audience an opportunity now to ask questions of the panelists. And if I'll come around with the mic, and if you don't mind just identifying yourself and then posing your question. So I'm ready. Howard? Okay, sure.
I'm Howard Lattin, professor of law at lovely romantic Newark. And I'd like to point out that none of the comments you've heard had anything to do with climate change or referred to climate change and its possible effects on the storm. In the last week or so, both Governor Cuomo of New York and the Mayor Bloomberg have both attributed the severity of Sandy to, at least in part, climate change. And as I'm sure all of you know, the American government has done virtually nothing to deal with climate change in a serious way. And they won't until scientists and other experts start attributing bad results like droughts and wildfires and hurricanes and tornadoes to climate change. I think everyone agrees that you can't specify one particular thing and say that's the result. But if you look at the pattern, then you can say that this is the result of a number of consequences of climate change. So what I'd like to ask is, do you think that scientists have reached the point yet where they're prepared to say that as a pattern, not necessarily as an individual event, that the kinds of 100-year storms that we're having every year or two now do reflect climate change and that they're going to get worse as the ratio of greenhouse gases in the atmosphere continues to increase. Thank you.
So if any of you guys want to grab that one.
I'll start. I've given about, of my 80 interviews in the last 2 weeks, I'd say about the last 5 in a row in the last several days have all been, lessons learned, looking to the future, and have involved lengthy discussions about climate change, partially spawned by Governor Cuomo, Mayor Bloomberg, and what have you, but just the natural thing that comes along. And Kerry alluded to it in his presentation earlier, that you can't take, and as you said, you can't take one storm and ascribe it. One thing you can do is look at sea level, and Ken will attest to the fact sea level was higher for this storm than it was in '62, and it was 100 years before that. Of course, that pales in comparison to the fact that it's hit at astronomical high tides and at high tide. But still, all those extra inches make a big difference in some cases in who gets flooded out and not. So I think what you can see here, we've had many extremes in New Jersey in recent years, mostly of the freshwater flooding variety. And you can begin to see a pattern of extremes, but by their very nature, extremes are rare. So as a climatologist, sometimes I ask for patience, but the public and politicians don't have much patience. So you've got to look now at whether we are changing the system enough that we're making these storms more frequent in terms of the magnitude of the storms. As I said earlier, the depth of the low pressure, the magnitude of the winds, the strength, the size of the tidal flooding. How much are we adding to each of these? They would be there without a human influence, perhaps, but are we adding to them? And as Kerry said earlier, are we changing the path of these storms? So climatologists, meteorologists, I think everyone up here on this panel is starting to talk to people. They're being asked questions, and we're speaking out about it. But it's a slippery slope there with how far you go, and you have to judge on where your credibility is going to be. If you come out and say it's all about this or none about this, where do you draw that line in the middle somewhere so that you're considered a credible source who knows what they're talking about? So we still are kind of talking around this situation a little bit, but it's not being ignored. I think that's the take-home point more than ever.
Do any of the other panelists want to respond?
Somebody.
I just want to remind people that weren't there, Rutgers Climate Institute sponsored an extreme weather event back in, when was it, Tony?
In March?
March, right.
Yeah.
And Becky gave a very good talk about extreme events and a relationship to global climate change and warming. And basically, it's like rolling loaded dice is the analogy. But the best analogy he quoted was from Tony, and this to answer your question about any singular event.
Here we go.
And that is that the Barry Bonds analogy. And basically, answer this question: which of Barry Bonds' home runs can be attributed to the fact he took steroids? He hit more home runs because he took steroids. There's no doubt about that. But no single home run, no single Sandy can be attributed to global warming. And I think that that's the teachable moment, and use that analogy. People just, I get it.
Yeah. Other questions from the room? Yeah, let me just do.
Robin?
I'll do Barb first.
Robin, can I follow up on?
Oh, yeah, one more. Okay, one more follow-up, and then we'll do the next one.
Just one thing. Put this right. There are good reasons for doing all the things that we would do to respond to climate change anyway. And people in my field who have been trying to get communities around the world to improve their protection against natural hazards and disasters frequently will ride along on the climate change debate because it reinforces the need for doing what we should be doing anyway. And to some extent, given the fact that already you have 90% plus by many estimates of the world's atmospheric scientists saying that they believe that what we're experiencing are the leading effects of global change, I'm not sure that the question is maybe the most productive question to ask. How do we get everybody to step out there and uniformly say that? We're always going to have some climate scientists who will probably not agree with others. And I think we've reached the point where we should be trying to address the benefits of proceeding in a way that has been described as sustainably for a whole variety of purposes, of which coping with climate change is just one. And I think one of the mistakes we're making is we're putting all our money on this one argument that we should be doing things to raise the general level of security in an uncertain environment by hanging it just on climate change, but certainly add climate change into the mix.
So I'm Barbara Turpin. I guess what we started to talk about just now is science communication and communicating a very complicated science that we don't fully understand. And so one of the other areas that this has to be done involves cancer and cigarette smoking, so lung cancer and cigarette smoking. Same situation, right? If you get lung cancer, maybe it's because you smoked, maybe it's not because you smoked. But that communication has been very successful on the public. And in fact, so successful that lawyers have won court cases against large tobacco companies over it, despite not really understanding the pathways. So I wonder if there are lessons we can learn from other complicated sciences in terms of communication.
I think if I may speak on this, I think your analogy is very good and very telling. I came across a headline in the New York Times from the year 1953, reporting on a conference of biomedical researchers those days who, I think for the first time, had come to a very powerful consensus that there was a connection between cigarette smoking and lung cancer. That was in 1953, front page of the New York Times, and 6 days later, there was a meeting of the heads of the big tobacco companies who decided to hire a public relations firm to persuade Americans that that was not the case. And it was a very effective campaign of disinformation, having some of the same elements that you see going on today with respect to climate. And per capita smoking in the United States peaked not until the 1980s. So you might say that this marketing, it's a science, by the way, marketing succeeded in a 20-year or 25-year delay between when science had pretty much established something and when the public accepted it. And as you point out, they ultimately did accept it. The tragedy about the present case is we're seeing the 25-year lag, maybe it's even longer, an even more, much better funded disinformation campaign from industry, and it's working. Everybody in this room, and there are probably people in this room who are skeptical about climate, but everybody certainly knows people who are. These aren't crazies necessarily. These are some of our friends, relatives, they're intelligent people who have been led to believe that there's no problem by an industry that has a lot of stake in that. So the communication problem for us as scientists is we can't go out and hire public relations firms and spend billions and billions of dollars. How do we communicate without exaggerating or going into territory we shouldn't go to counter that? And nobody has really solved that problem. I think that's the issue for our time.
Okay, other questions? Judy, go ahead.
Hi, I'm Judith Weiss. I'm a biologist up at Newark campus. Given the timing of this conference and Sandy, I was wondering if it might be of use, if people think it might be a good thing to do, to have a statement to the powers that be in New Jersey to say that when the shore is rebuilt, that it shouldn't be just business as usual, that they should take into account the likelihood that there will be more storms, more severe storms, and for sure, more sea level rise. And in rebuilding, it shouldn't be the same kinds of structures in the same places and business as usual, that there should be some smart thinking going into that. And I mean, we have a bunch of us here from Rutgers and elsewhere in the state. We could put out a statement. I think Tony could phrase it probably better than I, in such a way that is not saying, you know, you got to have X rules and move houses so far back. Nothing like that, but just a general statement. And I ask the group if you think that's a good idea.
And if anyone wants to react or respond to Judith's suggestion, the panel, in addition to the panel.
I'm going to give a quick answer. Oh, sorry, you have one back there. I think we should let that person go. Yeah.
I went to Rutgers as an adult, graduated psychology and comp-sci. I had the privilege of having Professor Robinson as a teacher. And Frank Malone was on Squawk Box this morning. Anyone watch Squawk Box? Becky there is like Squawk Box. She went to Rutgers. It's about business. And Becky from Rutgers asked Frank Pallone, what are we going to do? What? Okay. What are we going to do about the shore? How are we going to rebuild and restore it? Now you have to remember, we got Pallone in. He's a Democrat. He went to Aberdeen. It's demolished. He's talking about his section. He's talking about traveling all over New Jersey. He is a politician. He's saying that some residents want to buy back. They want the government to buy their land. They're not going to rebuild. Some residents that have been devastated want to do it on pilings. They will not leave. Christie said in the past, it's up to every individual. She asked more questions, and he's being a politician. Basically, they're waiting to find out what to do to see whether they're going to get money from FEMA to give 100% compensation instead of partial compensation. They're working on that right now. They're working on getting tents and housing and trailers, maybe in Port Monmouth and Fort Dix. They're working on that now. So they're working on survival right now. But their attitude is they're going to see how it goes and see how the residents respond. They need more hard information as to what to do with these areas. They're not going to move as politicians until scientists or somebody say, this area you probably can't rebuild on because of geological situations. So they're going to go the way the people go that bought the land. And that's my comment.
Any other responses to that comment? That's it. Are we going to start a new question? New question?
Well, before we go, let me just say one thing on that. I had a conversation with congressional staffers a few years ago, and I ended exactly as I ended my statement of what we should do going forward, and that is that there are certain areas that should be identified as areas that once the houses are destroyed, that they shouldn't be rebuilt. And the reply from the congressional office was, we would never get reelected in this district again. That said, this is a new time, and in fact, it was a Congressman Pallone's office. And so I do think that there is an opportunity here to open up this dialogue.
Let me just say very quickly that while I agree with Governor Christie that we shouldn't be telling people what to do, I would remind him that the rest of us shouldn't be subsidizing their choices. And that's the root of the problem. By capping insurance premiums on the coast, which is a politically motivated, non-free market kind of idea that somebody like Christie should be opposed to, by providing federal flood insurance, which is a massive subsidy to live in risky areas, and by bailing people out after the fact, we're subsidizing risky behavior. So if we stop doing that, if we stop the subsidies, people's behavior will change in response in ways that will be good for them and for the environment. And I think I agree with Ken that while politically it's very difficult to do that, if there was ever a time to do it, it's now.
I would want to make a point to follow up on that and agree with the general sentiment, but point out a couple of things. One is that the buyback programs have been persistently underfunded by the federal government, so that relatively few houses that would qualify because of high risk and damage more than 50% of their value actually get purchased and cleared. But you can point to certain communities where that has been very effective. But I would say you'd be talking about adding something to the national budget, which gets us into another major area of controversy at this time if we emphasize the buyback consideration. So that's just a sort of point of information while agreeing with the general sentiment.
Sid Madison, my understanding of the science is that inertia will cause all of these problems to increase. So how do you buy the hypothesis that as you explain, as you have these public appearances, you explain inertia so that people understand that it's going to get much, much worse? Is that a hypothesis that's workable in terms of increasing the value of your communication?
Well, I think that when I give talks on climate change in general, I stress something that my colleague Susan Solomon always stresses, is that the lifetime of carbon dioxide in our atmosphere is measured in thousands of years. And there's a lag in the system, which I think may be what you meant by inertia, so that decisions we make today are going to affect the climate hundreds and maybe thousands of years from now. We don't have, unlike the cigarette smoking thing, when the population stops smoking, 20 years later, the cancer incidence really starts to precipitously drop, which happened. But with climate change, there's a lag in the system, and if we don't make these decisions in pretty soon, it will be too late. And it's very important that we get that point across. I agree.
Hi, Peter Sugarman. Based on what we're hearing now, huge population along the coast, our approach is typically evacuation and emergency response. This might be more of an engineering or economic question, but is there some Patriot missile solution, a big, the Dutch-style model? Is that possible for the East Coast, or, to put up some dike system to prevent the next big storm, or is that just discussion right now?
I'm not an engineer.
Well, just along that sort of analogy, though.
I'm not an engineer, but I'd point out that the Dutch started building the massive dike systems along the mouth of the Rhine after the 1953 storm. And about a couple of decades later, they hauled off on enthusiasms for further large-scale schemes, and they decided not to dam the north coast of the Netherlands, the Waddenzee area, which had been scheduled for reasons that are very complex, include ecological oppositions, include political opposition, including no need to protect land that wasn't being used in agriculture, and so on. So if you think of the Dutch example as some sort of standard that should be adopted more widely, you should also ask the question, why is it that the Dutch have become less enthused about that kind of solution for their own protection? And I'm not here saying that it doesn't work for limited circumstances. It certainly does to protect limited areas. But as a general solution, and the Corps of Engineers, by the way, once had a plan to build not dams, but a groin system at, I believe it was something like half-mile intervals along the whole of the Atlantic coast of the United States. So there are lots of large-scale schemes like this that have been out there, but I would be careful about promoting them without carefully understanding how they're working in the places that they'd been adopted before.
You're also talking about the magnitude. Bound Brook was mentioned earlier, and there's now flood protection around Bound Brook. Of course, that's getting cries from people up and downstream that it's affecting their floodwaters. But that system was born of a flash flood, even before Doria in '71, a flash flood that killed a half dozen people in 1970, and it's just getting completed now. And it's just one community along the Raritan River. I'm not saying you should shy away from Herculean efforts, but consider the magnitude of that, and just even go down to the coast now, and Ken probably knows more about this than I, with the debates over building out the shore, sand replenishment, and the lawsuits and the hearings that have been held from one community or one homeowner to another in terms of protecting their part of the shore and the free access to it by the public if public funds are given to protect it. So I'm not saying you shouldn't think big. I mean, let's think big. You start somewhere and then you go from there. But the magnitude of what we'd be facing along the nation's shorelines is rather daunting.
In New Jersey, Warren Pilkey, famed coastal geologist from Duke, has dubbed Seabright the poster child for how not to do things. The seawall was built 100 years ago to protect a train. Of course, in every storm, including this one, they send a cub reporter down saying, "I'm reporting from the wall, Seabright," as the waves are breaking across the wall. The wall exacerbates erosion. We insist on putting sand in front of that wall. That's almost insane. What we should do at this point, since we've gone down that road, is basically finish the seawall so this community is protected, but that is now and build the wall up higher in a Dutch solution, basically making it a walled city, a dike city, really, a walled city. For the rest of the Jersey Shore, for the barriers, the only solution really is either retreat or nourishment. Do you think we're going to retreat politically? Do you think we have a prayer of retreating politically? So what we're going to have to do is continue to massive beach nourishment projects. And right now, the Army Corps is marching down, like painting the Firth Bridge, and does one community, moving further down, and then targeting especially prone areas like Strathmere and Atlantic City for targeted beach nourishment. But if these barriers are going to continue to have dwellings on them, that's the only solution.
I'm Greg Mountain, Earth and Planetary Sciences. 5 or 6 weeks ago, a judge in Italy sent a chilling effect through the geophysical community by putting 6-year jail sentences on geophysicists who were reluctant to predict an earthquake that had devastating consequences for a small town in central Italy. And it speaks to this same issue here, that we as scientists are in the business of understanding how the world works and making predictions about how it will behave in the future. I ask the panelists here, who are at various levels of forecasting, from the daily, weekly, to the centennial scale of forecasting the future, do you or do your colleagues have concerns when a microphone may be thrust in front of you, asking, well, what's going to happen next? When do you think the next big storm's coming? What should we do about it? And if you do have concerns about that, do you have anything to share with us, the rest of us, who in our own way are often given a microphone of sorts to make predictions about where our science is going, and in particular with those that have environmental consequences and human consequences? You must all have had some opportunity to consider this concern about how we bring our science to bear on the human scale.
Anyone want to start on that one? Or a piece of it?
Or we said climatologists make forecasts on time scales to which they can't be held accountable. But that's not really true, Greg. You're right. I guess I often use the line when I'm talking about, say, sitting on a drought commission in the state, whatever that, well, I'm a tenured professor. But at the same time, no, it's a serious consequence. There's the political forces out there that can put pressure on you if you speak out too much, and as you said, the legal system can as well. I've never been that concerned about that, but I've seen cases in other states when state climatologist was ousted because they dared talk about drought in their state, and the green industry, the horticultural industry, which has a powerful lobby, knew the governor, and the state climatologist at a university professor was released. You don't ever see this in the paper, but it happens. So yeah, I do get nervous about things like speaking out too much and saying the sky's fallen, and then having people look at their business or their interest and taking exception to my potential overstatement of the issue. So I think you have to, despite the fact that we're sitting here tenured professors, you have a responsibility to be a little careful with what you say, if not for your profession, perhaps for your own personal well-being.
Go ahead. All right, I'm going to just get to sea level and the predictions thereof. You're all aware of North Carolina. The Blue Ribbon panel convened, made certain recommendations. They were probably a little high in some of their estimates, calling for as much as, I think, 7 feet by 2100, which is certainly on the high end, as you can see from our poster here. But the backlash of basically being the King Canute of sea level will not rise anymore was passed in lieu law in North Carolina. So we do need to be careful about exaggeration. But Tad Pfeiffer from Penn State gave the NI lecture at AGU last year on how do we talk about possibilities, a prediction of the future. How do we pass along this information? And on my poster is also a little plot, and it's just a Gaussian distribution, and it's for sea level, and it has for 2100, and it has as the peak there around a meter, which is what is probably our best guess, and that's what it is really, folks. Going that far in the forward, it's really an educated guess, 3 feet, okay? Could it be as high as 7 feet? Possibly. It's a very low probability, as he would say. If you're an engineer and doing risk assessment, you need to plan for 7 feet. If you are a policymaker and looking for policy, you should probably be planning for 3 feet. In New Jersey, a bit higher. And so for 2050, a scientist like me shouldn't be saying a number like this. You really shouldn't, because you have to put error bars on it and specify it. But to communicate with policymakers, the error bars, they didn't just make it sound like you're speaking gobbledygook. So you have to come up with a number or a consensus of a planning number. And so again, for 2050, 1 foot would be what I would plan for. So the longest mortgage you're going to have here is about 30 years, 2040. You should plan for an additional foot based in terms of where we're going forward. So that's what I was alluding to earlier. So there's an example of a number that a scientist can put forth. Again, if we try to go with the higher numbers, and Warren Pilkey is out there also saying, could be 7 feet. Well, could be. It's unlikely. And that's where we have to be careful, because then it becomes, as our own Dick Lindzen would say, right, alarmism. And we have to be careful to walk that fine line between raising the alarm and being alarmist.
So I would just want to say that a lot of the discussion today, including this recent question about the prosecution of the seismologists in Italy, is all about communication and about the problems we scientists have communicating. We get in trouble. Our senators, U.S. senators, say that people like me should be prosecuted for being alarmist. And in Italy, they got in trouble for not making a prediction. So you can lose either way. But all of it boils down to a problem that I think was early identified by the author C.P. Snow in his famous Two Cultures essay from 1959, which was a shocking separation out in our culture of science and math from just about everything else. And the root of the problem is in the West today, not just in the U.S., but elsewhere. It's perfectly possible to become a top-notch lawyer or politician or something like that and know almost nothing about science. And when we have a situation where I think there are 2 scientists, 2 people with scientific background in all of Congress, maybe it's 3, does anybody know the answer? It's a very tiny number, and almost nobody else capable of understanding the concept of uncertainty, it makes the communication problem almost impossible. I mean, we're always inventing ways of getting across uncertainty. And, you know, people who look at the climate problem actually say there's a probability of outcome, and there's a cost of the outcome, and the cost of the outcome is extremely asymmetric. As you go out to the tail, the 7-foot end, the costs of dealing with that should arise are astronomical compared to 2 or 3 feet. And so it has to be, this has to be considered. We have to talk about the 7 feet at the risk of being labeled alarmists. But if we're talking to people who have no idea what uncertainty is, have no idea about how scientists treat uncertainty, in the end we fail. And so at the end, the only solution to that is for us as a society to insist that every person who wishes to call himself an educated adult have a little bit more background in basic scientific issues that include things like statistics and uncertainty.
Couple of points I'd like to add. One about the Italian court case and one about scientists and the politicians and uncertainty. As I understand it, and I've been talking with people in Italy who are closer to this than I think most of the media are, there are really two groups of scientists in Italy that were involved here. One was a group of scientists which made predictions about earthquakes, and another was a group of scientists that the government commissioned to report on the state of those predictions. And it was that second group that elected not to take the rather cautious stand that the first group had put forth, saying, yes, there indeed was possibility of earthquakes in Aquila, that is being prosecuted, that has been prosecuted. So it's really, they're being prosecuted less for making the prediction than for failing to pass along and correctly interpret the information that was given to them by the scientists who were making the predictions. And that, too, is a problem in communication, I think, as was raised, and communication is certainly very central to everything we're talking about here. The second point that I want to make about uncertainty is something that I remember learning a long time ago, which was that scientists place a great premium on the resolution of questions of uncertainty, reducing uncertainty. And politicians try hard very often to maintain uncertainty because it gives them maximum flexibility to introduce political considerations. And when scientists are asked to resolve what are in effect political problems, and they do so by saying we're reducing the uncertainty, that's not likely to be the key that opens the door. You have to have an appreciation for a much more, what I would regard as an ambiguous framework that surrounds everything that we do with regard to risk in the environment, and a multiplicity of interpretations of what scientists think of as risk. There are many other forms of interpretation of these things. So I think we need to broaden the framework of the public understanding of science, certainly, but the scientists have got to understand how to couch their messages in far more different streams of information aimed at different target audiences also.
My name's Lisa Auermuller. I work for the Institute of Marine and Coastal Sciences down in Tuckerton at our Jacques Cousteau Reserve facility down there. And my question is actually right along these same lines, which is my job is to work with coastal communities and bring them science-based information so they can make better informed choices. And I thought about Dr. Emanuel's talk and the paper he mentioned in his talk from Lynn, 2012, talking about the storm surge that New York City saw. And I think none of the community leaders in New York City would ever think to read that paper, nor would they know about it, or even know that that journal probably existed. So how can you, as scientists working with people like myself and others in the room, do a better job to work together so that we can help bring this message to the communities in a way that they can understand it?
I just would point out a bit of a paradox that paper was published in a journal called Nature, which is a sort of a broadly circulated, and we get criticized routinely by our colleagues for publishing results in what they regard as sensationalistic journals. So we get it from both sides. We're pandering to the public by publishing in a journal like that. And as you correctly point out, it's not going to get read by. The news there is actually a little bit more optimistic in that some of the people in the government of the city of New York had been aware of and working with people, particularly at State University of New York and Stony Brook, on surge risk in New York City. And in fact, before Sandy, were engaged in thinking seriously about barriers and so forth. So I think there was some attention to the risk, but what was missing from that was the urgency of it. I mean, who could predict that Sandy would happen so soon? But yeah, we wish that could be better. We really do. I wish I knew the solution to that problem.
I think you need to get out there away from just the journals, Lisa, as you're suggesting, and talk to the media, because they talk to a lot of people. People are out there in our communities in blogging, Real Climate, and they're geared at different levels. Some are geared at more the scientific level, some at more the public level. There's been a lot of commissions. New York City's done a good job in New York State in looking at climate change. State of New Jersey has put some effort, but not nearly enough into it at this point, and things get delayed in the political process of getting even published with some of the panels we've sat on. There are a number of people in this room guaranteed to sit on advisory committees. So I think we do, as scientists, educators, citizens, have an obligation, if we know something and have some thoughts, some knowledge, and some informed opinions about them, to speak out. And we're doing that. Many of us are testifying before state committees and things of that nature. So yeah, there has to be that step away from just the pure academic publishing and out there into your communities and giving presentations. And people ask me sometimes, how come you're not more alarmed when I'm talking to a group about what's going on with the climate system? I said, well, I could be back in my office reading my email right now, but I've come out to talk about it. And everyone has a different approach and demeanor in how they make their point. And I give everyone credit for however they wish to approach it. But you need to get out there. You got to get out from the tower and talk to the media and talk to the citizens out there and talk to the politicians and so on and so forth. I think it's a personal obligation for all of us.
Most of the people here have some science background or scientific interest, and I encourage you to be vigilant, to look at the blogs, to go to What's Up, Anthony Watts's blog, where so much, I won't even say it's disinformation, facts that are there, and find out the spin and what the answer is. And I got into this business as a geologist coming in from deep time. Okay, I'm a poser in that sense. I'm not a climatologist. But I've learned so much, because I was interested in sea level, learned so much from the people in this room, whether it be Tony Broccoli, whether it be Dave, Bob Kopp, others, that I've learned so much from. And broadening, and we're scientists, and we should, as Dave said, we need to get out, and out of our own niche too, out of our comfort zone. And you have to be careful, because you don't want to be saying the wrong thing. But there's tremendous resources here at Rutgers University and in the nearby region, whether it be at Princeton, GFDL, whether it be up at Stevens. And I think this meeting is exactly what Rutgers should be doing and must continue to do going forward. Every time I come to one of these climate meetings or the Rutgers energy meetings that we've been holding, I'm really proud of this university for taking us forward. And I think maybe the next step is to have this type of meeting here, but with GFDL, with Stevens, with other universities, with Monmouth University in this region, to have more of a regional get-together. And the idea is for us all to get to know each other and know that the guys, Jim Wright said so well this morning, to get to know that there's a guy over in Cook campus that does basically LIDAR approaches, which it was a pleasure to work with Rick Lathrop, who's on our poster here, in terms of predicting where sea levels was at. 5 years ago, I didn't know Rick from Adam. Okay, and it's because of this Climate Institute and because of the Rutgers Energy Institute that I've been broadened, and I want to thank them both.
I'm Margaret Conroy. I'm in the graduate program in ecology and evolution, but I'm also an actuary. So to talk about the comments that have been made about the politicians and their lack of knowledge of science, really, we don't need to have scientists necessarily go into politics or politicians necessarily go back and study science. We could just have them vote for the free market and let people do their jobs. For instance, actuaries do understand uncertainty and can affect the market because, as a lot of people have pointed out, if people actually had to pay the costs of living in risky areas, if municipalities had to pay the costs and weren't getting bailed out by the federal government when they put infrastructure in bad places, if people had to pay the ecological costs when they build ridiculous dikes or seawalls that are just going to cause more problems in other places, some of the science then could be shared indirectly with the public, and the policies wouldn't necessarily have to change, but the effects would be that people would change their behavior on their own because they were pushed to do so through the free market, having to pay for their own mistakes. So that's one way that scientists, climate scientists, could work with other people, other mathematicians or statisticians who understand that uncertainty principle, who understand that your sea level might rise 3 feet, but if there's a possibility of it rising 7 feet, then you have to put that into your price for insurance. So people will be then responding to that as well. So just a comment.
That's good, great comment. Does anyone want to have a response to that one?
Just to say that I wholeheartedly support that. I think, the idea that states can regulate insurance premiums, and we think of another industry in the United States where we would allow that to happen, which is not to say we should not have any regulations, but to regulate rates is to stop a free market price signal from getting to the place it needs to get to, which is the homeowners. And we do this systematically through the United States, and it's anti-American, and it's crazy, and it's part of the problem. So I completely support that. We just need to set that part of the market free if we can.
I learned this from Tony, is that it's important as scientists to stay as politically neutral as possible. And we had, and I will say it was a pleasure to meet, Tony and I, with Governor Christie and Department of Environmental Protection Commissioner Bob Martin a year ago. And this is after the governor had made his somewhat infamous statements that he wasn't sure global warming was real. We reached out to him, and Tony in particular was very successful in convincing the governor. Whatever you think of Governor Christie, he's no dummy. He's a smart guy. And he listened, and he learned. But he is a politician, and he walked out of the meeting, and he gave the party line that he believed in global warming, and it was likely attributable to humans. He could have been on the IPCC. But then he turned around and said, well, we're pulling out of Reggie. And then he turned around and said, no new coal-fired power plants in New Jersey. So 2 steps forward, 1 step back, and that's the nature of politics. So I regard that as a success. We went probably better if we had not pulled out of Reggie. That's, as I told the governor, that's basically a political and economic decision. But you can communicate with your legislatures. You can walk in to your legislature's office in any time. You can go to Bob Menendez's office, you can go into your local legislature, and I encourage you, if you go to Washington, to take that half of a day and go do that, or a few hours. And that's really important. They listen. They listen, or write to them. Okay? Write to your local representatives in Trenton. They don't get much mail. They'd love to hear from you, and you can have a real impact. Don't think you don't. You won't. You will.
Okay, I think we maybe have time for one more. Anyone? Okay. Okay. All right, a quick.
The position that the free market is going to help might apply to adaptation, but it does not apply to mitigation. And anybody that thinks it does, sitting in this room, doesn't understand global warming. Mitigation has to be handled not by the free market, but by national laws.
Yeah.
I think you guys heard that one even without the microphone.
Yeah, just I wanted to come back on something about the free market and the National Flood Insurance Program, because there were some statements made earlier about, and with many people make them, about how the availability of flood insurance encourages development on the coastal zone. You have to remember that the flood insurance program will only compensate homeowners and small business owners up to $250,000 for the value of property that's lost. And many of the properties on coastal lines are multi-million-dollar properties. So taking away the flood insurance program probably won't have that much effect. It'll just allow people who are already willing to sink that amount of capital into developing the shoreline to do it, and it'll strain out a few people at the bottom end who probably wouldn't be able to afford it without the flood insurance. So you'll have a generally a rise in the scale of development to large scale, much richer, much more capitalized developments on the coast.
I have a comment and a question, or just sort of a follow-on from the discussion. And I'm not a scientist, I'm a social scientist, so maybe that makes me feel quite free to talk about politics. And I understand why scientists with their scientist hat on might be careful about doing that, but in terms of policy, I think it's inescapably political. So just the comment is that, just to, I don't think it's the case that to regulate the insurance market is anti-American. And in fact, we're having a national debate and discussion about health insurance. And one reason why we have this sort of hybrid free market national regulation is because I think our president agrees that we're a rich enough society that nobody should have to die on the street from, pancreatic cancer or something like that just because they have no resources. So turning to the Jersey Shore, I think that the impacts of this disaster are not equally felt, and that the communities and individuals don't have equal resources to respond. So to sort of step back from that would be to say, and to let actuarial realities fall where they may, would be, as I think the last comment was going in this direction, to sort of turn the shore over to those with deep pockets. And so I guess that's a comment. Then as a question, looking at what kind of advice or what kind of policy direction to go from, going back to earlier comments that suggest that certain places should not rebuild and that standards should be raised, much higher than they are. I'm curious about how confident, coming back to prediction, you all are that if you were in the governor's chair and you could just implement that, you would be able to make really positive recommendations, because there was the finding that those communities that had better prepared for this storm and those that had not really didn't show, there was a very random or unpredictable outcome. So do you feel like if we put together the best understanding, the best models that we had now, you could, as a planner, sort of lay out, okay, these are the places along the shore that should not be rebuilt, and these are the standards that we would have to implement to have not put people in harm's way, or, and therefore the insurance standards could reflect those and direct people to build in a safe way?
I just comment that Ian McHarg, when he wrote his book Design with Nature, laid out a plan for much of the Jersey Shore that would probably look something like what you're advocating. And a few years ago, I guess, must be about 20 years ago now, there was one of Orrin Pilkey's volumes written on New Jersey, with a number of Rutgers people on it, including Carl Nordstrom from our geography program, Living with the Jersey Shore, which identified most of the areas that are at highest risk and that were damaged in this last storm. So I think there's no shortage of information about how to identify areas at risk. The problem is and always has been translating that information, making good use of the science. I was involved with something called the International Decade for Natural Disaster Reduction years ago, and our philosophy was that what we really needed around the world was putting to work all the unused knowledge that simply wasn't being used. And if you did that alone, you would have a material impact, at least on the natural hazard loss totals around the world. So I don't think it would be difficult to do what you're suggesting.
Let me reply a little bit about when I got emotional before, is because in Waretown, which is one of the poor communities on the Bay side, between Barnegat and Forked River, where we are. Most of the houses that were in harm's way were still on ground level. And from the 1980s on, you were required to build your houses on pilings 9 feet up. And so, yes, that's a policy decision. That is a zoning decision that was made. Basically, the Department of Environmental Protection is the one who sets those flood levels. That has a tremendous impact and is done by regulation. The towns have a tremendous power in zoning in order to require larger lots. Unfortunately, that's a double-edged sword, because ultimately, as you increase the lot size, and you're favoring the rich and that are able to afford it, and as Ken pointed out, the same thing with the insurance, until the self-insure. So the idea, though, that there are areas of following the Bound Brook analogy of saying no rebuilding is where we should go, but I don't think in this country that that's going to be tenable in any case. We are just too much with the property rights of an individual in this country.
All right, well, I think we're going to wrap up the panel now. Just 2 takeaway points. One, we are certainly going to be talking a lot more about what to do with the Jersey Shore and how to redevelop it. I think that probably has its own space for a forum. And then I think I was really struck by how many questions that we're still raising about communication and science around these issues. This is actually now our 3rd event where we've been dealing with this. We had one 2 years ago on science and communication around climate change, last year on uncertainty, and now partly what this panel was devoted to. So I think those are certainly topics that we have there's a lot of questions about, and a lot more need for discussion and commentary. So I'm going to turn it over now to Bob Kopp just to introduce our afternoon session, but maybe we can just all thank the panelists for a really great job.
Hi.